This is my beginning algebra course. In the last class, we introduced square roots, and we learned how to simplify expressions with square roots by using addition and subtraction. In today's class, we're going to continue to simplify expressions with square roots. Specifically, we're going to multiply and divide square roots. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. As you can see, we're going to multiply these square roots. And to do that, we're going to use the principle that we learned in the last class, the principle in green here, except we're going to go backwards. Instead of going from this direction, from here to here, we're going to go in the other direction. We're going to go from here to here. So instead of breaking the root into two roots, we're going to take two roots that are multiplied and combine them to one root. So square root 2 times square root 2 is going to become square root 2 times 2. So again, the 2's will be considered A and B, and you just put them together under the root. So now we can go ahead and simplify. 2 times 2 is 4. But we know what the square root of 4 is. That just asks what number times itself is equal to 4. What number times itself is equal to 4? Well, the answer obviously is 2. So as you can see, when you multiply the square root of a number times itself, you get the number under the square root. So let's try number 2. Square root 6 times square root 6, that's going to be square root 6 times 6, which is square root 36. And the square root of 36, that would just be 6. So what you're doing here is you're doing the opposite of this of a square root. The opposite of square rooting is when you square a number, but when you square a number, you're just multiplying it by itself. So you're getting rid of the square root. All right, I'm going to drag this over here. Let's try number 3. We're going to use the principle in green. And that would be, if you get your calculator out, that would be 169. And that's a perfect square, so it would end up being 13. If you don't believe me on that, you can just get your calculator. It's going to be exactly 13. So now it's time for you to try. Try number 4. When you come back, we'll do it together. All right, we're back. So if you got that answer, good job. Try number 5, and when you come back, we'll do it together. All right, we're back. So if you got 5, good job. Now you're probably wondering, do I have to show these steps? Because it's obviously just going to be 5. Well, in today's class, I'd like you to show the steps. When you go into upper mathematics, even when you go on to other parts of this course, I'm not really going to require that you show the steps because it's just it's not necessary. But in today's class, I'm going to require you to show the steps. So try number 6, and when you come back, we'll do it together. All right, we're back. So if you got that answer, good job. Try number 7, and when you come back, we'll do it together. All right, we're back. Again, we're using the green principle here. That's why I keep dragging it around with us. And what number times itself is equal to 64? Well, that would be 8. So again, when you multiply square roots together, you just multiply the numbers inside the square roots together, and you keep a big square root over it. So try number 8, and when you come back, we'll do it together. You might have to use a calculator to find 11 times 11. All right, we're back. That would be 121, and the square root of 121 is obviously just 11. All right, so I think you get the point. Why don't you try numbers 9 and 10, and when you come back, we'll do them together. All right, we're back. So at this point, well, I guess we're just going to keep going here, because I think it's best for you to show the steps. And 14 times 14. Let me get my calculator out because I'm not sure what that would be. That'd be 196. Yeah, we're just showing the steps. So if you got those answers, good job. Try number 11 and number 12, and when you come back, we'll do it together. All right, we're back. So if you got that answer, good job. Let me get my calculator out. 17 times 17 is 289. And square root of 289 is 17. So if you got those answers, good job. So now we're going to do something different. In the previous problems, we multiplied square roots where the numbers under the roots were the same. And you realize that we just got they just took away the square roots, because squaring is the opposite of square rooting. So if you square a number, you just multiply it by itself. And if you're not sure what I'm talking about there, let's say that you have x to the second power. That just means x times x. So if you have square root x to the second power, that just means square root times square root. So that's what we did. And we got square root x squared, which just became x. So when you square, that's just the opposite of square rooting. So it just gets rid of the square root and you're left with the original number. That's why we had root 10 times root 10 is equal to 10. It just gets rid of the square root. So that's a very important concept. So now we have different numbers under the root. So how do we deal with that? Well, we just use the green principle again. It's no big deal. We're going from here to here. So we're starting with two roots, and we're multiplying, and we're combining them into one root. So that would just be root 3 times 2, and then we just simplify, and it becomes root 6. So as you can see, it's pretty easy. Now again, do you have to show this intermediate step? I think in this class it's probably best that you do. But again, when you go into upper mathematics, even further on in this course, this very course, you're not going to have to show every intermediate step. All right, so number 14. Again, I'm going to use this principle going in from right to left. And we have root 10. I'm just going to put that negative out in front because that negative is not inside the root. And then we get root 70, which cannot be simplified. Let's try a couple more of these together. So root 7 times root 2. Again, that's just going to be root 14 because you're just going to multiply 7 times 2. But I'm just going to show that intermediate step. And there you go. So hopefully you have the point by now. And why don't you try number 16? And when you come back, we'll do it together. All right, we're back. So we get negative root 10. So if you got negative root 10, good job. As you can see, this stuff is fairly easy so far. So why don't you try number 17, and when you come back, we'll do it together. All right, we're back. So negative times a negative is a positive, and then we end up with root 11 times 3, which is root 33, and we're done. There's nothing we can do with root 33. So if you got those answers, good job. So now we're going to go to something a little different. You'll see what I mean as we do the number 18. So again, we're just going to combine into one root, and we end up with root 18. The problem is there's a perfect square in root 18. Mathematicians don't want you to leave perfect squares as factors inside roots. So what we're going to do is what we did in the last class. We're going to factor to 9 times 2. Now, why did I factor to 9 times 2? Because 9 is a perfect square. Neither 3 nor 6 were perfect squares, but when I factored 18 to 9 times 2, now I have a perfect square. Now, why is that a perfect square? Well, remember from the last class, we had that list of yellow numbers. I'm going to drag it over here. These yellow numbers are perfect squares, and as you can see, 9 is in that list right here. So I'm going to use this principle. So first I went from right to left to go from here to here, and then I'm going to go backwards. I'm going to go from here to factor out a 9. So I went in the reverse direction, and now I'm going in the forward direction. If forward is left to right and reverse is right to left. So now root 9 becomes 3, because it's a perfect square. What number times itself is equal to 9? Well, that's 3. So if you're not sure about what I'm doing here, then you probably need to go back and do the homework from the last class. If you didn't do that homework, you'll learn nothing in this class, the last class, or any class in any math course at any time in history. You have to do that homework or you're going to accomplish nothing. All right, so number 19. We'll do that one together. So again, you just use the green equation there, combine into one root, and then you get square root 50. But now I know I have a perfect square in here because I know that 25 times 2 is 50, and I know 25 is a perfect square. So I'm going to use the green principle. I used it in the reverse direction, then I used it in the forward direction to get a different factorization. So now, square root 25 is just 5. What number times itself is equal to 25? Well, obviously that would be 5. So you get 5 root 2. And we can't do anything with the root 2. Remember, we learned that from the last class. We can't do anything with that because that is an irrational number, meaning the decimal is not going to repeat, it's not going to terminate, and it's not going to have any kind of pattern to it. So we can't write it easily. All right, so again, you want to multiply those roots together, and then you want to pull out a perfect square. So now you try number 20, and when you come back, we'll do it together. All right, we're back. So now factor to 4 times 3. Again, 6 and 2 are not perfect squares, but 4 is a perfect square, so I gave a different factorization, and root 4 is 2, so you have 2 root 3. So if you got 2 root 3, good job. I'm going to bring all my equations down here all at once, because these are all important. We haven't used the blue one yet. All my equations and all my information I'm bringing down. We haven't used the blue one. We have used the green one quite a bit. All right, so try number 21, and when you come back, we'll do it together. All right, we're back. So now I'm going to pull out 4. I'm going to pull out the perfect square. And there you go. So if you got that answer, good job. All right, so try number 22, and when you come back, we'll do it together. All right, we're back. See, that's going to be 84, it looks like. You can get out your calculator if you want. But that doesn't really do us a lot of good to combine it, to multiply it to 84, because we're just going to break apart it apart and find a perfect square anyway. So it'd probably be better if we just took this and factored it to 4 times 3. So if I factor 12 to 4 times 3, I can see the perfect square is right here, the 4. And then I can recombine. So 7 times 3 is 21. So I took the 4, put it here, and I took the 7 and the 3 and combined it to 21. And yes, it is perfectly legal to do that. That's the commutative rule of multiplication. We learned that in my arithmetic course. If you didn't take my arithmetic course and you don't remember that, that's okay. All that means is that we're just changing the order of the multiplication, so we can combine the 7 and the 3. That's completely legal. So now we just take the factors apart, or split the root into 2 parts. And obviously I'm running out of room here, so I'm going to have to shrink this a little bit. And we have negative 2 root 21. So if you got negative 2 root 21, good job. All right, so now we're moving on to something even easier than that. We have, we're multiplying a root expression by a whole number. And so this is easy. We just do 7 times 10 to get 70. And we just put the root right next to it. That's it. Very simple. So that one really didn't require a lot of work. So why don't you try number 24. When you come back, we'll do it together. All right, we're back. We get negative 48 root 10. All I did was just multiply negative 8 times 6. So if you got that answer, good job. All right, so try 25, and when you come back, we'll do it together. All right, we're back. Negative 2 times negative 5 is 10 root 3, so if you got 10 root 3, good job. Try 26, and when you come back, we'll do it together. All right, we're back. And there we go. So if you got that answer, good job. All right, so now we're going to something a little different. So we're multiplying 2 root expressions together. Well, we actually did that in the previous problems. Whoops, sorry. Sometimes the program jumps around randomly. I don't know why. So we multiplied. You can see that the first problems we did, we multiplied roots together. We multiplied roots that were the same, roots that were different. The difference with the problems that we're doing now is that now you're multiplying expressions that have a whole number and a root. So this is very easy. You just multiply the whole numbers. 3 times negative 2 is negative 6. And root 5 times root 6, well, you can just put those together using the principle, the green equation. That's that green equation that I'm carrying around with me here. And then we get root 30. And there's no perfect square in 30, so we can just leave it as negative 6 root 30. Let's try the next problem. 2 times 6 is 12, and we just multiply the numbers in the root. And again, you will not need to write this intermediate step. When students in upper math courses do this math, they don't write this intermediate step. They just put everything together. So don't be discouraged because I'm having to write all these intermediate steps. You won't have to do that when you go into upper mathematics. So now we get 12 root 35, and there is no perfect square in root 35. Well, you might be wondering, how do I know there's no perfect square in 30 or 35? Well, 5 and 7 are prime numbers, so you can't factor those in any other ways. 30 you can factor to 2 times 15, you can factor to 6 times 5, you can factor to 3 times 10, but you can see there are no perfect squares in any of these factorizations. So as you learn more and more about these numbers and the different factorizations, you will start to be able to identify quickly whether there's a perfect square as a factor. And all you need to do is just try the different factorizations to see if you can find a perfect square. All right, so it's time for you to try. Try number 29, and when you come back, we'll do it together. So if you got that answer, good job. All right, try number 30, and when you come back, we'll do it together. All right, we're back. And it doesn't matter how you factor 42, you're not going to find a factor with a perfect square. You can try to factor 6, so you get 2 times 3, and then you can recombine, so 7 times 2 is 14, then your factorization becomes 14 times 3, so on and so forth. You can try 2 times 21 by combining the 3 and the 7 to 21 and keeping the 2. But you can see that there's no perfect squares in any of those factorizations, so you can't pull out a perfect square. There is no perfect square factor. So if you got that answer, good job. All right, try number 31, and when you come back, we'll do it together. All right, we're back. A negative times a negative is a positive, and there is no coefficient here. It's assumed to be negative 1, so negative 2 times negative 1 is positive 2, and so on and so forth. As you can see, this stuff is pretty easy. It's easy if you do your homework, so you can remember how to do the problems, but if you don't do your homework, like I said, you will learn absolutely nothing. I promise you, you will learn nothing. All right, so why don't you try number 32? When you come back, we'll do it together. All right, we're back. So again, this is considered to be negative 1, so negative 1 times 6 is negative 6. And we're using this principle here. We're just going backwards. We're going right to left. It's extremely important to understand this green equation here. So negative 6 and then 2 times 13 is 26. And if you didn't know 2 times 13 was 26, you can just get your calculator. So if you got that answer for 32, good job. All right, so whoops, I realized I accidentally put the answer right there. All right, so let's do number 33, take it step by step. The difference with this problem is that when we multiply those roots, together, we're going to get we're going to get a number that has a perfect square as a factor. So we're just going to have to do more steps on this one. But it's the same procedure. Negative 3 times 6 is negative 18, and we have root 2 times 10. The roots just combine into one root based on this green equation. So then we get negative 18 times root 20. Now 20 has a perfect square. So I'm going to factor the perfect square, 4 times 5. Then I'm going to use the green principle in the forward direction and break it up into 2 roots. And then root 4 is just 2 because that's a perfect square. So again, remember we learned how to take out a perfect square of a root expression in the last class. So 4 is a perfect square. Why? Because it's on this list. If you square the whole number 2, you get 4. Negative 18 times 2 is negative 36. And the 5 just has to stay inside because it's going to be, root 5 is going to be an irrational number. So again, it's the same exact thing that we did in the previous problems. The only thing is we had to do an extra step because there was a perfect square inside the root. So let's try number 34 together. Negative 2 times negative 8 is positive 16. And then we have root 15 times 3. Now, neither 15 nor 3 are perfect squares, but if we combine them together, we get 45, and I recognize 45 as 9 times 5, and why is that significant? Well, because 9 is a perfect square. You should also be aware that you don't have to multiply these two numbers to get 45. In fact, it's kind of dumb to do that, because what you can do is you can take 15 times 3 and you can factor 15 to 5 times 3, and then you can combine 3 times 3 to 9. So you don't have to go to 45 and then factor backwards, but the only problem with doing it this way is that a lot of students get really confused. So I didn't mean to say that it's dumb for you to do it. I meant it's dumb if you know how to factor and you're taking advanced mathematics. At this level, it's probably easier and easier to explain just to multiply and then use your multiplication facts to go backwards. All right, so now we're going to use the green formula in the forward direction and take out that perfect square. 16 square root of 9 is 3. 3 times 16 is 48. So if you got that answer, well, actually you didn't do that one on your own. So all right, so I think you got the point. So try number 35, and when you come back, we'll do it together. All right, 2 times 7 is 14. And we have root 30 times 5, which is root 150. Again, I'm just going to go in the forward direction. I'm not going to do that crazy factoring because, again, it kind of confuses students. So now, what do we have here? I think we have, there's a lot of different ways to factor it, but again, it's hard to factor it from this point. It's easier to factor from here. But I do know that 25 times 6 is 150. So that saves me because I know 25 is a perfect square. And let's see, the square root of 25 is 5. And 5 times 14 is 70. And you can get your calculator out if you don't want to do that on paper. 5 times 14. So if you got 70 square root 6, good job. All right, try number 36, and when you come back, we'll do it together. All right, we're back. I'm going to refactor to pull out a perfect square. I'm going to use the green equation. So we got negative 48 square root 2. Good job. All right. On to number 37. So why don't you try number 37, and when you come back, we'll do it together. All right, we're back. 3 times 24. That would be 72. Now, a lot of students are going to try to factor 72 to 9 times 8. But the problem with that is that 8 has a perfect square inside it. I mean, 9 is a perfect square. So you can take 9 out. That's correct. But 8 also has a perfect square. So you don't want to do it that way. You want to do it a faster way. You want to factor 72 to 36 times 2. Now, is it wrong to do 9 times 8? No, it's just you're going to have to pull out a perfect square 2 times. Remember, we talked about that in the last class. But if you factor it to 36 times 2, you only have to pull out a perfect square 1 time. So it's just less work. The problem is it's harder to factor to 36 times 2 than it is to factor 9 times 8 because 36 times 2 is not one of our multiplication facts, whereas 9 times 8 is. So, in case you didn't understand anything that I was talking about there, I just want to show you what it would look like if you tried to factor out a perfect square twice. So let's factor it to 9 times 8 instead of 36 times 2, and I'll show you all the steps that you have to do. So we're going to break it to 9 times root 8, and then we get 10 times 3, which becomes 30, but now we still have a perfect square inside the 8, and that's the problem. So we have to keep going. We have to do it again. So now we're going to factor 8 to 4 times 2, which becomes root 4 times root 2. Root 4 is 2. and we get 60 root 2. So we had to do all these extra steps because we decided to factor the 9 times 8. So what you want is a number that's a perfect square, in this case 36, and a number that is neither a perfect square nor does it contain a factor that's a perfect square. The problem with 9 times 8 is not that you have a perfect square, because you want a perfect square. The problem is the other factor contains a perfect square as a factor, which means you're going to have to factor out a perfect square twice. I know that's a lot of stuff to explain, but the most important thing is that you know how to do the problems. You don't have to give it some elaborate explanation. So if you got 60 root 2, good job. So now let's try 38. And when you come back, we'll do it together. All right, we're back. This one's actually going to be pretty easy because we're going to get square root 36, but 36 is a perfect square. So that's just going to be 6. And let's see, 6 times 28, you can get your calculator out if you want, but that would be 120 plus 48, so 168. So if you got 168, good job. So now we're going on to something a little different. We're going on to distribution. We're going to use the distributive property with square roots. No big deal. Remember, if you have a and you multiply it times the sum b plus c, then you just use the distributive rule. You multiply a into b, and then you multiply a into c. And then you add the products up. So root 3 times 5 is 5 root 3. It's traditional to write the whole number farthest to the left. And then 3 times 6 root 6, well, that's just going to be 6, and then 3 times 6 inside the root. So now, so again, we took root 3 and multiplied it by 5. We took root 3 and multiplied it by this expression here. So we can't do anything with 5 root 3. We'll change that to 6 root 18. And now I'm going to have to factor out the perfect square from 18. So that would be 9 times 2. And we get 6 times root 9 times root 2. And 6 times 3. Square root of 9 is 3. And we get 18 root 2. So it's just the same thing that we did in all the previous problems. The only difference is we're using the distributive property. So why don't you try number 40, and when you come back, we'll do it together. All right, we're back. Root 4 root 2 times 3 is equal to 12 root 2. 4 root 2 times negative 6 root 3 is equal to negative 24. I'm going to have to move this over. Negative 24 root 3 times 2. So where did I get the 3 times 2? Well, because you're multiplying root 3 times root 2. Let's see. All right, so I'm going to keep going here. The rest is pretty much the same thing that you've done. So root 3 times 2 is root 6, and that's actually it. We can't go any farther than that. So if you got that answer, good job. All right, on to number 41. So we have more problems with the distributive rule. The only difference is we're going to multiply a monomial by an expression with 3 terms. So that just means you multiply this term into this term, and you multiply that same term into this term, and that same term into this term. So distribution works with an infinite number of terms. It doesn't have to be 2 terms inside here. So 2 root 2 times 3 root 6 is 6 root 12. And 2 root 2 times negative 7 root 3 is negative 14 root. Actually, you know what? I should show the intermediate steps for that. I'm sorry. That should be 2 times 6. And then negative 14 root 2 times 3. And 2 root 2 times negative 5 root 7 is negative 10 root 2 times 7. So let me just double check that. Make sure I didn't make any dumb mistakes. Everything looks right. I'm just going to move this over a little bit. And then we can go ahead and combine. And the only thing that we can do now is we have a perfect square here, because I know that 4 times 3 is 12 and 4 is a perfect square. Six times 2 times root 3. Then we get 12 root 3 minus 14 root 6 minus 10 root 14. I think you got the point. Just double checking that. Everything looks good. So all we had to do there is pull out the perfect square. So why don't you try number 42. And when you come back, we'll do it together. All right, we're back. So 5 root 2 times 3 root 6 is 15 root 2 times 6. 5 root 2 times 7 root 2 is 35 root 2 times 2. And so on and so forth. And we'll refactor 12. And root 4 is just 2. What number times itself equals 4? That's 2. 4 is a perfect square. So the root just goes away. It's extremely important to understand that if it's a perfect square inside the root, then the root just goes away completely. We're using the green principle here. 35 times 2 is 70. And there's nothing we can do with negative 50 root 14 because root 14 is an irrational number. 14 is not a perfect square. Now if that were 16, then we could find the square root. That would just be 4, but it's not 16, it's 14. 14 is not a perfect square. But root 4 is a perfect square. And 15 times 2 is 30. And that should be our final answer. So if you got that answer, good job. All right, so now we're going on to division of square roots. We're pretty much done with multiplication. As you can see, multiplication is really not that big of a deal. We use the green equation here in the previous problems. But now we have to go to the blue equation. Now we used the blue equation in the last class as well as the green equation. So we're used to these formulas. But in this class, like I said, we went in the opposite direction. In the previous class, we went from here to here. In this class, we had to go backwards. Well, it's the same. The same is true for the blue equation. We're going to have to go backwards in the blue equation. So we're going to start from here, and then we're going to go to here. So you can see that we have root 15 over root 3. That's like root A over root B. So we're just going to go backwards, and it's going to become one root. So we're going to combine the roots into one root, just like we did in the previous problems. For example, we multiplied root 6 times root 6. We combined two roots into one root with multiplication. Well, we can do the same thing with division. We can combine two roots, 1, 2, into one root. Again, there's no mystery here that we're just using the blue equation like we did in the last class. We're just going backwards. That's the only difference. So now all we have to do is just simplify the inner part. 15 divided by 3 is 5. And we just end up with square root 5. And then we're done. Because there's really nothing we can do with square root 5. It's an irrational number. We can't pull out a perfect square, so on and so forth. So that's all we're doing in these problems. Let's try one of these together. In fact, we'll try two more together before you try one on your own. So we're going to combine to one square root, and the negative just hangs out there. And 20 divided by 5 is 4, so we have square root 4. But there's a difference here because square root 5, 5 was not a perfect square, but 4 is, so we can keep going and make it 2. So 2 is the final answer for that one. So that was a little different because we came up with a perfect square. So let's try one more of these. This problem was going to be a little harder because when we combine to one square root, we're going to find that our number, after simplifying, contains a square root or a perfect square as a factor. So we combine to one square root, and the negatives, negative divided by negative just is a positive, so those go away. And then 56 divided by 7 is 8. So again, we're combining to one square root, and then we are simplifying the inner part. That's the whole point of these problems, is to combine and simplify the inner part. So now it's simpler. But the problem is, in this problem, we have a perfect square as a factor because I know that 8 is 4 times 2. So now I'm using the green equation. So now I'm going to use, from here to here, I use the green equation. So root 4 is 2, and that's why we took it, we factored it, because the perfect square, the 4, comes out. And we're left with 2 root 2. So now it's time for you to try. Try number 46. And when you come back, we'll do it together. All right, we're back. So if you got root 6, good job, because 12 divided by 2 is 6. And remember, a division or a fraction symbol can be interpreted as division. We talked about that in previous courses. All right, so let me drag our equations up here and on to 47. So now it's time for, let's see here. Yeah, now it's time for you to try. Try 47. And when you come back, we'll do it together. All right, we're back. So we get root 80 over 5. And if you use your calculator, you know that 80 divided by 5 is 16. But that's a perfect square. So square root 16, what number times itself is 16? That would just be 4. So if you got negative 4, good job. That negative should be closer to the 4. All right, try number 48, and when you come back, we'll do it together. All right, we're back. combined to one square root, and 60 over 5, that would be 12. And 12 has a perfect square, so we have to factor out. We have to factor the 4 times 3. Using the green equation, we end up with 2 root 3. So we got 2 root 3. Good job. All right, try number 49, and when you come back, we'll do it together. All right, we're back. Negative divided by negative is a positive. 75 divided by 5, I believe, is, well, actually, we can just combine first. 75 divided by 5 is 5. And there's nothing we can do with square root 5. Try number 50, and when you come back, we'll do it together. All right, we're back. The negative hangs out in front because, again, the negative is not inside the root. Don't try to put that negative inside the root because that would create a serious problem. When you have a negative inside a square root, we have what are called imaginary numbers. We're not going to cover those until my intermediate algebra course. 75 divided by 3 is 25. So that's a perfect square. And again, you can use your calculator for this if you don't want to do that on paper. So we get negative 5. So we've got negative 5. Good job. All right, so we did some division problems. Now we're going to go to something that is related to division. We have some fractions here, and what we're going to do is called rationalizing the denominators. Now I want to explain something here. If you try to divide 86, for example, by 5, that's not that difficult to do. You can do it using long division. But what if you try to divide 86 by 56, for example? That would be a lot harder because there's a 2-digit divisor. That would be very, very difficult. You could do it, but it would take a lot more work. But what if we have a more difficult situation? What if it's 568 divided into 86? Or maybe if this number were even bigger, imagine how difficult that would be. Now you have a 3-digit divisor. So when the dividend is a big number, that doesn't really make our calculations that difficult. It's when the divisor is a large number that makes things really, really difficult. So we learned in the previous class that when you have a root 5, and again, a fraction sign is considered to be division, so we're technically dividing 3 by root 5. But we learned when you have something like root 5, that's an irrational number. So if I plug in root 5 into my calculator, what I get is, and again, you want to push the 5 button and then push the square root button, and I get what's called a decimal that doesn't terminate. So 2.236067, so it just keeps going on and on. So imagine if we had to divide 3 by a divisor that just keeps going on and on. That would be very difficult because, again, when the divisors are large numbers, it's very difficult to do those calculations. So we don't want an irrational number, a root, inside the denominator of the fraction because that just makes calculations difficult. So what we're going to do is we're going to do a little trick, and we're going to get rid of the root in the denominator. It's called rationalizing the denominator. So again, the important thing for you to understand, if you didn't understand any of that explanation, that's okay. The important thing for you to understand is we don't want roots in the denominators of fractions. Mathematicians do not like roots in the denominators of the fractions. So what we're going to do is we're going to rewrite the fraction, and we're going to use the fundamental principle of fractions to get rid of that root. Now I just want to review. Let's say you have the fraction 4/7. You can use the fundamental principle of fractions to make those numbers bigger. For example, you can multiply both sides by 5 to get 20 over 35. 20 over 35 is equivalent to 4/7. At the same time, you can divide both of these numbers to go back to 4/7. You can divide both sides by 5. So the fundamental principle of fractions, which you should know like the back of your hand, says that if you can multiply both the numerator and the denominator of a fraction by the same number, and you get an equivalent fraction, meaning the value of the fraction doesn't change. We learned that in my arithmetic course, and you should know that for my pre-algebra course, and also this course we talked about it. And you can also divide both sides of the fraction by the same number, and the fraction remains the same value. So we're going to use that fundamental principle of fractions to get rid of that root 5. So here we go. Instead of multiplying by a whole number, we're going to multiply by root 5. We can multiply by anything pretty much, and the value of the fraction will not change. So we're going to multiply both sides of the fraction by root 5. Again, this is the fundamental principle of fractions we're using here. We're just multiplying both sides of the fraction by the same number. No big deal. So the big question is obviously, well, why do we do that? How does that help us? Well, again, we're trying to get rid of this root. Watch what happens. So we can just get rid of that dot in the numerator. It'd just be 3 root 5. Remember, you don't need a dot between the whole number and the root. And so then in the bottom, we're going to use the green equation. You see the green equation here? We're going to use that green equation, and we're going to combine to one root, and we get root 5 times 5. And then we have 3 root 5. We'll just rewrite the denominator, and root 5 times 5 is root 25, and I think you can see what's happening here. This is a perfect square. 25 is a perfect square, so root 25 is just 5. So we use the fundamental principle of fractions, and we change the form of the fraction so that there now is no root in the denominator. And that makes calculations much easier. So again, that's called rationalizing the denominator. So if you didn't understand some of that stuff, that's okay. We're going to do some more problems. So again, we have a fraction on number 52, but the fraction is not rationalized. The denominator is not rationalized because there's a root. We don't want that root in the denominator. So we're going to rewrite the fraction, and we're going to use the fundamental principle of fractions to multiply both sides of the fraction by some number. And again, as long as that number is the same, it's not going to change the value of the fraction. So then we get 2 root 3, and root 3 times root 3 using the green equation is root 3 times 3. And root 3 times 3, that would just be root 9. And root 9, what number? That's a perfect square, so that you just end up with 3. What number times itself is equal to 9? Well, that would just be 3. So again, why did we do all that? Well, because in this form, we had a root in the denominator, but in this form, we don't have a root in the denominator. We have a root in the numerator. And it's okay to have a root in the numerator, we just can't have one in the denominator. So again, this fraction is equivalent to this fraction, meaning they're the same value. So if you plug in 2 divided by root 3 in your calculator, you'll get the same number that you will if you plug in 2 root 3 divided by 3. But the calculator may have some trouble calculating this because, again, the divisor is such a long string of digits. All right, so why don't you try number 53, and when you come back, we'll do it together. All right, we're back. So if you got that answer, good job. All right, so why don't you try number 54, and when you come back, we'll do it together. All right, we're back. So I'm sorry about this, but I didn't predict that we're actually going to have to do one more step here. Do you see these two numbers? We can reduce this fraction. So I'm sorry I didn't tell you about that. If you got 8 root 6 over 6, that's perfect. Good job. But we just have to reduce it. So you can divide both these numbers by 2, and then you get 4 root 6 over 3. And no, you're not going to divide the 6 inside the root by 2. Root 6 is a factor. So if you divide an expression that's factored by some number, you don't divide both factors, you just divide one or the other. So 4 root 6 over 3. All right, so try number 55, and when you come back, we'll do it together. All right, we're back. Use the fundamental principle of fractions. So we got that answer. Good job. All right, try number 56, and when you come back, we'll do it together. All right, we're back. Four is a perfect square. But this is another example where we can reduce the fraction. 6 divided by 2 is 3. So we just end up with 3 root 2. So if you didn't go to that last step, that's okay. Now you know. We can reduce fractions sometimes. All right, so if you got 6 root 2 over 2, good job. You just had to reduce at that last step. All right, on to number 57. So we're going to be doing the same principle. We're just going to have some extra steps. So let's do 57 together. Again, we're going to rationalize the denominator. We have a root in the denominator. We don't want a root in the denominator. So we're going to get rid of that root in the denominator. But in these problems, there's actually two things that we have to do. We have to get rid of the root and the denominator, right? But we also have to pull out the perfect square in the denominator. I know that 24 has a perfect square because I know my multiplication facts. I know 4 times 6 is 24, and 4 is a perfect square. So the big question is, which one do we do first? Do we get rid of the root in the denominator? Do we rationalize the denominator? Or do we pull out the perfect square? Well, actually, you can do it either way. I think that pulling out the perfect square first is going to be the easier method. Let's see here. Actually, I'm having second thoughts. Maybe in this problem, pulling out the perfect square or rationalizing would be easier. Let me think about this. Well, I guess it's about the same either way. I'm going to go ahead and just pull out the perfect square in the first step. So we've done this many, many times. I'm going to factor 24 to 4 times 6. And I did that obviously because 4 is a perfect square. I'm going to use the equation in green, the green equation over here. Remember that equation. You got to keep that in mind. Whoops. And we have root 4 times root 6. And so I pulled out the perfect square. Root 4 is a perfect, or 4 is a perfect square, and root 4 is 2. So all I did was I pulled out the perfect square in the denominator. That's all I did. All right. So, but the problem is, we solved the first problem. We got rid of the perfect square in the root. But the second problem still has not been solved. We still have a root in the denominator. We don't want a root in the denominator. We're going to have to rationalize it. So we're going to have to use the fundamental principle of fractions to multiply both sides by root 6. And again, you must multiply by root 6 because we have a root 6 in the denominator. That's the only way to get rid of the root on the 6 is to multiply by itself. So now 3 times root 6 is 3 root 6. And with this problem, we've done this problem before. When we have a root multiplied by another root, we just multiply the roots together. So the 6 times 6, they become 1 root. We're using the green equation in the reverse direction. And obviously, 6 times 6 is 36, and you can see where we're going with this. The root in the denominator is about to go away because 36 is a perfect square. So we can find the square root of 36 very easily. What number times itself is equal to 36? Well, obviously that's 6. The square root of 36 is 6. And we just have, we'd have to multiply 2 times 6. Whoops. 2 times 6 is 12. And then 3 over 12 we can reduce. 3 over 12 just reduces to 1 over 4, but we don't have to write the 1 here. Remember, we can just write the root 6. So there's a lot of steps there. Now I know what you're thinking. You're thinking, I don't like this at all. There's too many steps. I don't want to write all that stuff out. It seems really difficult. Well, I want you to understand very clearly that I'm only showing the steps to help you figure this out. You don't have to show all these steps for this particular problem because there's just too many steps. Now, obviously, if you get confused, then you're going to have to show the steps just so you don't confuse yourself. But when you get into later parts of this course, and especially upper math courses, you don't have to show every step. If you showed every step of this problem to your teacher would be very concerned that you would take too long to solve the problem, and he would take up too much paper. He would tell you, I don't need you to show every single one of these steps. So you don't have to do that when you get into upper math. What you would do is you would show everything up to this point. And in fact, I just remembered, or I just realized, I probably should have shown an extra step there. I'm sorry about that. I just missed one step there. We have to write the result. I didn't really miss a step. I just didn't preserve the result of the previous step. So then we end up with 3 over 2 root 6, and then after that, then you multiply both sides by root 6. So I kind of got ahead of myself. All right, so you have to show this step. You have to show from here to here, and then you have to show from here to here, and then you have to reduce. So those are the only parts that you really need to show for this. So I don't want you to become nervous or anxious about this because there's so many steps. You really don't have to show all these steps. So I know earlier in the class I said that you do have to show steps, but when it comes to this huge mess here, you don't have to show all those steps, unless, of course, you're confusing yourself and getting the wrong answer. Then you might have to show every single step. All right, so I'm just showing you those steps so that you know what's going on. So let's try number 58 together, and you can try some other problems, these other problems on your own. So again, I can rationalize the denominator first, or I can pull out the perfect square. I'm just going to pull out the perfect square. I don't want to do it both ways because I don't want to confuse you. All right, now there's an extra step here. We can actually reduce. Negative 6 over 3 is negative 2. You can always reduce if you need to. I mean, you can't always reduce, but I mean, if you can reduce, then you always need to reduce if you can. All right, So we took care of the first problem. We now have pulled out the perfect square from the root. So we're done with that problem. And this time, before I rationalize the denominator, I'm going to rewrite. That's what I forgot to do last time, so I'm going to rewrite. And then I'm going to multiply both sides by root 5. And why root 5? Because there's a root 5 in the denominator. The only way to get rid of it is by multiplying it by itself, because that's the opposite of square rooting. Again, if you don't understand what I just said, that's okay. To be quite honest, most students don't understand. They just want to know how to do it. And as long as you know how to do it, you're fine at this point. And so we get negative 2 root 5. Root 5 times 5. Root 25. Root 25 is 5s. So there you go. So it looks like that problem didn't take quite as many steps. That's because we had a 3 cancel out here. That's why it didn't require so many steps. All right, so now it's time for you to try. So try number 59. I'll try to keep these problems in the window here. There's 57 and 58. And when you come back, we'll do it together. All right, we're back. So I'm going to pull out the perfect square first. Again, we have 2 problems. We have a perfect square inside the root, and we have a root in the denominator of the fraction. We have to deal with both of those problems. And I've taught you how to pull out the perfect square first, and then deal with the root in the denominator on the second step. So now we cannot reduce 2 over 3, so we can just leave that fraction. So now we're going to deal with the, we just finished. We finished taking out the perfect square out of the root. So now we're going to multiply both sides by root 6 to get rid of the root in the denominator. We're going to rationalize the denominator. Now we get 2 root 6 over 3 times root 6 times 6. Again, we use the green equation, this green equation up here, to combine those. And we get 2 root 6 over 3 times root 36. And of course, the reason we did this is because when you multiply root 6 times root 6, it just gets rid of the root, because root 36 is just 6. That's the whole point. So we've got a couple more things to do. First of all, we have to go ahead and multiply. 3 times 6 is 36. Well, I mean 18. But then we have one last thing to do. We can actually reduce 2 over 18. So that's going to be 1 over 9. But we don't have to write the 1. We don't have to write the 1 here. We can just write root 6 over 9. It's very unusual to write a 1 next to a root. And if you become an engineer, they're probably going to laugh at you if you do that. They're going to say, why did you do that? That's not unnecessary. All right. It's not really wrong to put a 1 there. It's just very, very, very unusual. So if you got root 6 over 9, good job. So all kinds of things are happening there. We had reducing and rationalizing the denominator and pulling out a perfect square and so on and so forth, using the fundamental principle of fractions. So try number 60. And when you come back, and by the way, 125, if you don't know how to deal with that, you can just bust out your calculator and you can divide by 5, whatever you want to do. That'll help us figure out what that would be. So try number 60, and when you come back, we'll do it together. All right, we're back. So if I use my calculator, I know that 125 is, whoops, I don't know why I did that. You know what, I just realized I added an extra step here. I don't know why I did that. I just rewrote the same thing over again. I'm sorry about that. I should move that up. You don't really need to do that. Sorry if that confused you. You know what, I did the same thing on this problem. I'm sorry about that. Over here, I just rewrote the same exact thing. I'm sorry if that confused you. So I did an extra little line there. All right, so 9 over root 25 times 5. Again, I can divide 125 by 5 to figure out that it's 25 times 5. And again, we're pulling out the perfect square. That extra step I did there, that wasn't a big deal. It was just I rewrote the problem for some reason when I didn't really need to. No big deal. It's just the same steps to follow there. All right, so root 25, we pulled out the perfect square because root 25 is just 5. So we took care of the problem of a perfect square in the root. So now we need to take care of the problem where we have a root in the denominator. We don't want that root in the denominator, so we have to multiply both sides by root 5. And we get 9 root 5 over 5 times root 5 times 5. And so on and so forth. And root 25, we can find that number. That's just going to be 5. And 5 times 5 is 25. So we got that answer. Good job. Let me just double check that. Everything looks right. All right, so on to number 61. We have the same type of problems here. So go ahead and try 61, and when you come back, we'll do it together. All right, we're back. Four times 7. We pulled out the perfect square. Now we're going to rationalize the denominator. We have root 7, so we must multiply both sides by root 7. So now we rationalize the denominator. The only problem is we can reduce that fraction. Sorry if the page is a little too far zoomed out there. 6 over 14, divide both by 2, and you get 3 over 7. So 3 root 7 over 7. So we got 3 root 7 over 7. Good job. Again, don't be nervous because of the number of steps here. You don't have to show every step. I'm just showing you the steps so that you don't get confused. Once you understand it, you can skip quite a few steps. So try 62, and when you come back, we'll do it together. All right, we're back. We're going to get rid of we're going to pull out the perfect square first. Whoops. There I go, rewriting the same thing again. So you could factor it to 6 times 3, but there's no perfect square in 6 times 3. So we have to factor it to 9 times 2. And you could put the dot in between the roots, but you really don't need to. (8√2). I'm trying to keep the entire problem in the view, but I really should zoom in because it's hard to see what's going on. 3/√2 times 2. (3√4). Root 4 is a perfect square, which is why this whole thing works. Square root of 4 is 2. We learned that in the previous class. Three times 2 is 6. Divide both sides by 4. And we have 4√2/3. So we got that answer. Good job. All right, try number 63, and when you come back, we'll do it together. All right, we're back. So we pulled out the perfect square. Now we just have to rationalize the denominator. So we have a √7, which means we have to multiply both sides of the fraction by √7. And we get -√7 over 3 times 7, because root 49 is 7. Root 49 is a perfect square. -√7 over 3 times 7, which is 21. And there's really nothing we can do at that point. Whatever you do, please do not try to reduce √7 over 21. It is true that we can reduce 7 over 21, but you cannot reduce √7 over 21. That's completely different. So this is the answer. Do not go any further with that problem. So if you got that answer, good job. All right, so try number 64. When you come back, we'll do it together. All right, we're back. (75) is 25 times 3. So now we pulled out the perfect square. Now we just have to rationalize the denominator. √9 is 3. But we can reduce 10 over 15, so that divide both sides of the fraction by 5, and we get 2√3 over 3. So if you got that answer, good job. All right, on to number 65. So now we're doing something different. In the previous problems, we had individual roots in the fractions. In fact, the first fractions that we did, you can see we had 2 roots, and we combined them into 1 root. And in all the other problems, we had individual fractions, or excuse me, we had individual roots in the numerator of the denominator. But in these problems, we're actually going to go the opposite direction. Let me bring my equations down here. Sorry, my computer is lagging on me, jumping all around. Bring these equations down. So for number 65 and on, you can see we're going to be going backwards. We're going to be starting with one root. And we're going to be going to two roots. So we're going to be going in the forward direction as we did in the previous class. So we're going to go from here to here. So I'm going to make this root 5 over root 4. And of course root 4 just happens to be a perfect square, so I end up with root 5. There's nothing we can do with the root 5 because 5 is not a perfect square, but root 4 would be 2. So you're probably thinking, well, what was the point of that? Why did we do that? Well, that's going to come in handy. This is easier to deal with. When the denominator of the fraction does not have any kind of root in it, it's much easier to deal with. So the purpose of these problems is to, again, rationalize the denominators. If the denominator is under a root, then technically it's not rationalized. All right, so I'm going to try, let's see, I'm going to try 66. Again, we're using the blue equation going in the forward direction. We get root 41 over root 9. And root 9, or 9 itself, is a perfect square, so that would just be 3. So as you can see, these problems are pretty easy. But there's a lot of different types of these problems, so as you can see, this is about the 4th or 5th type of problem we've done. So that's going to be the hardest thing for you to do, is to figure out what exact method do we use to simplify these fractions with roots, or just to rationalize the denominators. So try number 67. Again, you're going to use the blue equation, and when you come back, we'll do it together. All right, we're back. So we got root 6 over 5. Good job. Try 68. When you come back, we'll do it together. All right, we're back. So we got root 10 over 7. Good job. Try 69, and when you come back, we'll do it together. All right, we're back. Using the blue formula, we get root 3 over 9. So if you got root 3 over 9, good job. Try number 70. When you come back, we'll do it together. All right, we're back. So we got root 19 over 6. Good job. So notice that in these problems, the denominators were all perfect squares. So when we use the blue equation, the denominators were instantly rationalized because they just ended up being a whole number: 2, 3, 5, 7, 6, 9, so on and so forth. But in the next problems, in problem number 71, the numerator is going to be a perfect square. So the numerator is going to immediately go into a rational number, a whole number, but the denominator is going to be irrational. Then we're going to have to rationalize the denominator. So let me show you what's going to happen here. We're going to use the blue equation again. We're using the blue equation. So we get root 9 over root 2. And root 9, the numerator this time, is a perfect square. So root 9 is 3. And the difference, again, you see the difference here? We have a root in the denominator now, as opposed to these previous problems where we had roots in the numerator. So what that means is we're going to have to do some extra steps to rationalize the denominators. We did not have to rationalize the denominators in these problems because they were already rationalized. But in number 71, we're going to have to keep going. So we know how to do that. We've already done that before. So just rewrite it, multiply both sides by root 2 because you have a root 2 in the denominator. And we get root 2 times 2. And that would just be root 4, and root 4 is 2. So we just had to do an extra step there to rationalize the denominator. So I'm going to try 72. Same situation. Root 64 is 8. But now we have to rationalize the denominator because we have a root in the denominator. So we use the fundamental principle of fractions. We get 8 root 5 over root 5 times 5, which of course is root 25. And root 25 is 5. All right, so on to number 69. Actually, I mean, sorry, 73. So we have the same problems for 73, so now it's time for you to try. Again, you're going to use the blue equation to split the numerator and the denominator into two roots. And then you're going to have to rationalize the denominator. So try 73. When you come back, we'll do it together. All right, we're back. So now rationalize the denominator. And I'm kind of running out of room here, so, well, I guess I have enough room. 7 root 6 over 6. So if you got that answer, good job. All right, try number 74, and when you come back, we'll do it together. All right, we're back. Root 16 is 4. Now we're going to rationalize the denominator. And I'm going to have to skip a step here and just write root 49. That's what I did in the last problem. I did it without even realizing I did it. Whoops, that should be 49, not 4.9. Because again, we're running out of room here, so you should be getting a hang of how to do this anyway. You can start skipping some steps if you feel comfortable doing that. All right, so try number 75, and when you come back, we'll do it together. All right, we're back. And, whoops, I skipped a step there. Well, actually, I guess I had to skip the step. I'm running out of room here. Sorry about that. So that'll be root 121. And 121 is a perfect square, so it just becomes 11 as usual. So we got that answer. Good job. Try number 76, and when you come back, we'll do it together. All right, we're back. Using the blue equation, And now we have to rationalize the denominator. And I'm just going to skip a step there, I guess. I mean, you could do 37 times 37 in your calculator, but you know that this is just going to end up being 37. So at this point, I'm going to skip a step there because we're running low on time, and you're going to need to start skipping steps anyway. All right, so in the previous problems, when we use the blue equation over here, there was always a perfect square in the numerator or in the denominator. But in these problems we're about to do, there's no perfect square in the numerator or the denominator. So these are going to be a little different in the way that we have to simplify them. Sorry about that. My screen likes to jump around for no reason whatsoever, randomly. All right, so we're going to use the blue equation here. And again, we want to rationalize the denominator. That's really the purpose of what we're doing here, is to rationalize the denominators. The denominator is inside the root. We don't like that. We don't like a root to be an individual. We don't like a denominator to be an individual root in this case. And we don't like a denominator to be in a root period in this case. I know that's kind of strange to think about, but that's just the situation. So now we're going to use the blue equation again, just like we did in the previous problems. And then we're going to rationalize the denominator just like we did in the previous problems. So obviously we want to get rid of the root 5, so we're going to multiply both sides by root 5. And up here, remember how you do this. You just use the green equation there. We already did this today. Same thing in the bottom. We use the green equation. And root 6 times 5 is obviously just root 30. And root 5 times 5 is just root 25. And then we have root 30. Root 25 would just be 5. So there you go. We rationalize the denominator. So same situation as before. The only difference is when we multiplied, we had a root in the numerator. So that root in the numerator, we had to multiply root by root. But we've already done that in this class, so that shouldn't be a big mystery. All right, so 78, we get root 5 over root 7 using the blue equation. Then we're going to multiply both sides by root 7 because we're trying to get rid of the root 7 in the denominator. And we get root 5 times 7 using the green equation, and root 7 times 7, again using the green equation. And then root 35 over root 7 times 7. 7 times 7 is 49. Root 35. Root 49 is 7, so root 35 over 7. So now it's time for you to try. Go ahead and try number 79, and when you come back, we'll do it together. All right, we're back. So I'm going to skip forward a little bit here because we're running low on time. So that would just be root 30 over 10. And so now if you got root 30 over 10, good job. You know what? I don't think we need to skip steps. I think we can show those. I guess we have enough time. I don't want to confuse you by skipping steps here. I'm going to write fast though. So again, if you got that answer, good job. Try number 80. When you come back, we'll do it together. All right, we're back. And 121 is a perfect square, so we just end up with 11. So we got that answer. Good job. All right, on to number 81. 81 is the same situation, so try 81, and when you come back, we'll do it together. All right, we're back. Again, I'm going through a lot of, spending a lot of energy to show every step here. I just don't want to confuse you. When it comes to roots, students get very confused very easily. There we go. So that one was a fairly easy one. So if you got root 6 over 3, good job. All right, try 82. When you come back, we'll do it together. All right, we're back. And you can use your calculator for 10 times 13 if you want, but just remember that when you multiply anything by 10, you just add a 0. And the square root of 169 is 13, and we cannot pull out a perfect square for 130. So if you got that answer, good job. All right, so for the next problems, we have a situation where the numerator is going to have a perfect square. So it's going to be the same procedure, but the numerator is going to have a perfect square that we're going to have to pull out. So we've got two problems. One problem is that we have to rationalize the denominator, and the second problem is that we have a perfect square we have to pull out. So let's get into it. Now, you can pull out the perfect square first, or you can rationalize the denominator first. I'm going to pull out the perfect square first because I think that would be easier. So we're going to factor 12 to 4 times 3. And then we're going to use the green equation to separate the root into two roots. And root 4 is 2. And now we're done at that point with pulling out the perfect square from the root. So now we're going to rationalize the denominator because we have root 5 in the denominator. We don't want root 5 in the denominator. So we want to get rid of the root 5, so we have to multiply both sides by root 5. And there we go. So let's try number 84. Again, use the blue equation. This is the blue equation over here. Factor 40 to 4 times 10. Use the green equation. And root 4 is 2. So we pulled out the perfect square from the root. But now we have a root in the denominator, so we have to rationalize the denominator. So we're going to rewrite and multiply both sides of the fraction by root 7 because we're trying to get rid of the root, the root 7. And there we go. So try 85, and when you come back, we'll do it together. All right, we're back. So if you got that answer, 2 root 6 over 3, good job. Now this may seem intimidating, but that's only because I'm showing every single step. Again, you don't have to show every single step. When you get to the point where you understand the principle, you can really skip a lot of steps. So try number 86, and when you come back, we'll do it together. All right, we're back. And of course, 121. Square root of 121 is 11. You can do it on your calculator if you want. So if you got 2 root 55 over 11, good job. Try 87. When you come back, we'll do it together. All right, we're back. Sixteen times 3 is the best factorization for that. You can do 8 times 6, but it's going to take a lot longer. Four root 15 over 5. So if you got 4 root 10 over 5, good. Good job. All right. So let's see here. I think I'm going to have to skip over that one. We can come back to it if we have time. All right, so these are the same exact types of problems, no difference whatsoever, except you're going to have to pull out a perfect square in the denominator instead of the numerator. So let's try one of these together. It's the same principle. Use the blue equation. And so now we're going to have to pull out a perfect square in the denominator. So we get 9 times 2 in the denominator. So we pulled out the perfect square. Now we just rationalize the denominator because we can't have a root in the denominator. So I'm going to start skipping steps here because we just don't have time to show every single step. Well, you know what? I can't do that. I don't want to confuse you. We'll skip some problems if we have to, but I don't want to skip steps in the actual problems. You can skip steps, but I don't want to skip steps at this point. And root 14 over 3 times 2, because root 4 is 2. And then we finally end up with root 14 over 6. So it's pretty much the same situation. See if you can try number 90. And when you come back, we'll do it together. All right, we're back. Use the blue equation. Pull out a perfect square. And we have root 5 over 2 root 3. And now we have to rationalize the denominator because you see that root 3 in the denominator? We can't have that. So we multiply by root 3 to get rid of the root 3. We end up with root 15 over, whoops. I'm so used to skipping steps myself that I have a tendency to skip. Root 15 over 2 root 9. Root 15 over 2 times 3. Root 15 over 6. So if you got root 15 over 6, good job. All right. So let's see here. Why don't you try number 91, and when you come back, we'll do it together. All right, we're back. Pull out the perfect square in the denominator. Root 9 becomes 3. Now we're going to rationalize the denominator. So if you got root 10 over 15, good job. All right, so we're going to have to skip 92, 93, 94. Hopefully you got the idea with those problems because we're running out of time here. We might go back to one of those if we have time, but 95 through 100, those are the last problems we have to do. So we did problems where you have to, again, we have a root over the entire fraction. And the numerator is a perfect square, so that immediately that makes the root go away in the numerator. We have the situation where the denominator is a perfect square, so the root in the denominator goes away immediately. And then we have situations where the numerator contains a perfect square factor, or the denominator contains a perfect square factor. And those are the ones that we just finished. But now we have a situation where you're taking the root of a fraction, and the numerator and the denominator have perfect squares. So this is going to be interesting. I know what you're thinking to yourself. You're thinking, I've had enough. Well, I'm sorry, but this is just what you're going to have to learn when it comes to roots. This part of the course where you have to learn roots, it's the part of the course that gets really tedious for students, but you just have to do it. That's one of the reasons beginning algebra is such a difficult course, is this root part of the course. All right, so root 27. Let me get my equations here. So we're using the blue equation, like usual. Like in the previous problems that we did, root 27 over root 20. I really need to write more legibly. And so we usually pull out the perfect square, but we're going to have to pull out perfect squares in both the numerator and the denominator. So there you go. No big deal. So now we just have to rationalize the denominator like we did in the previous problems, and then we're done with this one. So we're going to multiply both sides by root 5 because the denominator has a root 5. And we end up with 3 root 15 over 10. All right, so we're running out of time here. So why don't you go ahead and try one of these, see what you can do, and use this as a guide. And when you come back, we'll do number 96 together. All right, we're back. Pull out the perfect squares by factoring. Use the green equation. And there you go. We pulled out the perfect squares in the numerator and the denominator. So now I'm just going to rewrite to preserve the result of those previous steps. And I'm going to multiply both sides by root 5. So if you got 2 root 55 over 15, good job. All right, let's try number 97. And when you go ahead and try that yourself, and when you come back, we'll do it together. All right, we're back. Let's see, 56. We could do 8 times 7, but there's got to be an easier way to do this. So 8 times 7, let's factor that to 2 times 4. And then we recombine 4 times 14. So 4 times 14 is going to be the easiest way to do it. So that may have confused you, but again, sometimes you just have to factor and play around with the recombinations of the factors. Students really don't like that. They hate that because they get confused, but you're just going to have to get used to that. Again, you don't really need your dots here. I'm writing my dots sometimes, sometimes not. When you put something in front of a root, you don't really need a dot. All right, 3 root 7 over 2 root 14. And we're going to multiply both sides by root 14. So at this point, we pulled out the perfect squares. Now we're going to rationalize the denominator. And we have 3 root 7 times 14 over 2 root 14 times 14. So I don't know what those numbers are going to be, so I have to get out my calculator. And let's see, 7 times 14 is 98. So 3 root 98. And 14 times 14 would be 196. So root 196. Again, we don't really need to show that it's root 196 because we know it's just going to reduce to 14. This is going to be 14. All right, so we end up with 3 root 98 over 2 times 14, which is 28. Now there's one thing, 7 times 14 over here, 7 times 14, if we combine, because I suspect there's a perfect square in 98, so if we factor 14 to 7 times 2, you can see that we have 2 7s. We combine them, we have 49 times 2. So I'm going to go ahead and go backwards in the backwards direction and factor 98 to 49 times 2. Again, you don't really have to go forward and backwards. You can predict that. And then we have 3 root 49 times root 2, pulling out the perfect square. And I'm going to have to, I'm kind of going off to the side here. I'm going to have to do an arrow. Whenever you run out of room, there's really nothing you can do except just draw an arrow. There's nothing else to do. If you don't have any more room on your paper, what else can you do? So 3 times root 49 becomes 7. And we see here, let's see, I'm just going to multiply. I don't want to cause any confusion. So 3 times 7 is 21. But 21 over 28 can be reduced. We can divide both 21 and 28 by 7 using the fundamental principle of fractions. So we get 21 divided by 7 is 3. And 28 divided by 7 is 4. So that is the final answer. So I think that's the last problem we have time for. So that's plenty of work for you to get the hang of what you need to do. This is all the work that we did today. If you'd like to take screenshots of these pages to help you with your homework or to study for tests, go ahead and do that now. Don't go before you get your homework. Here's the homework. Get a screenshot of these first 2 pages. And these pages. And these last 2 pages. So get that homework done completely, correctly, neatly, and put it in order in your binder. And remember, if you don't do the homework, then you're not going to learn fluency in algebra. And that's the whole purpose of this course. Actually, today we weren't really doing any algebra, but the concepts that we learned today we're going to need for later classes in this course. So get that homework done, and I'll look forward to seeing you in the next class.